Welcome back. So the last time we discussed the one-variable inverse function theorem and its proof. I glossed over a little bit in its proof, glossed over a detail or two intentionally because I want you to get practice with one-variable calculus. Before we move on to the proof in more than one variable, which we'll do in a bit more detail. We then stated the multivariable inverse function theorem. Again, what does it say in words as opposed to writing things down? It says if you have a CR function, where R is at least 1, and if the derivative matrix at a point A is an invertible matrix, then this function is locally invertible, which means that there's a neighborhood around A and the neighborhood around f of A, so that f takes this neighborhood to this neighborhood in a one-to-one onto manner, and the inverse which exists is also CR. Okay, this is what it's stated. In other words, it's a local CR diffeomorphism. Locally it's invertible and the inverse is also CR. So that's the statement of the inverse function theorem in more than one variable. It only, to draw all these conclusions, all you have to do is to compute the derivative at a point and find out whether that matrix is invertible or not. Okay. By the way, given that the derivative, the inverse is differentiable, we know a formula for the derivative of the inverse thanks to the chain rule. We've already done that. So the question is, why is it locally invertible in the first place? Why do we care about this? This is the more important question, right? Here is a reason to care about this. For example, even in one variable calculus, consider this equation, which I'm writing down. Okay. So suppose you consider this equation, right? What is f of 1? This is f of x. This is 1. So the real question is, and what is f dash? It is 1 plus cos x e raised to sin x. So f dash of 1 is 1 plus cos 1 e raised to sin 1 by 100, which I claim is not 0. Okay, because 1 radian is like 50 degrees roughly, 50 or 60 degrees, 57. So this is anywhere positive, right? So it's not 0. Now the point is, by the one variable inverse function theorem, f of x equals c has a solution for all c sufficiently close to 1, right? So this is a very interesting thing. If you want to solve this equation, right, this is a remarkably difficult equation to solve. Of course, if c is 1, you have a solution, right? F of 1 is 1. But in general, it's not clear if you can solve it. But the inverse function theorem says that if c is sufficiently close to 1, then this equation does have a solution. It says a little bit more than that, but it says at the very least this, that you can solve an equation if you perturb the right hand side a bit under some circumstances, right? In higher dimensions, it's saying something even more non-trivial. In higher dimensions, so suppose you take a matrix, suppose this is an n by n matrix, and you want to solve this, right? So this can be solved for all b in Rn if and only if A is invertible. Okay, this is a theorem from linear algebra, right? You can solve this for all b if and only if a is invertible, and in that case the solution is actually unique, right? Why is this the case? Well, one way is to, for example, bring a to the row echelon form and then just check, right? So in other words, if you have a linear system of equations and the corresponding matrix is invertible, then you can solve Ax equals b for all values of the right hand side. And in fact, you can write a formula for the inverse for the solution, and x depends in a very nice manner on b, right? It depends in a smooth manner on b. What if you have a nonlinear system of equations? This is a linear system of equations, right? If you have a nonlinear system of equations, you can't always solve them, right? The inverse function theorem tells you something very interesting. It says, suppose you already have one solution, suppose you have this, right? If you perturb b a bit, you will continue to have solutions to this equation, provided the derivative at this point is an invertible matrix. Matrix implies that this has a solution for all b close to a, close to b naught, right? So you can always, if you perturb the right hand side of a nonlinear system of equations, you can solve it provided the derivative at this point is invertible. So in other words, basically, if you have n equations and n unknowns, under reasonable hypotheses, you can always solve them. Just like if you have n equations and n unknowns in linear algebra, as long as the equations are independent of each other, you can solve for x. The same thing holds in the nonlinear settings. If you have n equations and n unknowns, provided you already have a solution, as long as you perturb the right hand side of the equation a bit, you can still continue to solve provided the derivative is an invertible matrix at one point. Okay. So it's a nonlinear version of the common sense statements that if you have n equations and unknowns, typically you will end up having solutions. The number of equations matches the number of unknowns. Okay. Where is this coming from? What is an intuitive way to understand where the derivative being invertible is playing a role? The point is, f of x is approximately f of x naught plus the derivative at x naught times x minus x naught, right? So if you want to solve this equation, you're approximately solving this one. You already know that this is b, right? So this is b naught. So in other words, you want to solve this, and you can solve this precisely when this is an invertible matrix. You have reduced yourself to the linear case. In other words, a nonlinear function can be approximated by a linear function, right? And therefore, if the linear equation can be solved, then you can expect the nonlinear one also to be solved. This is the fundamental idea that's going on behind the scenes. The linear approximation of the nonlinear function, which is why we can only say b close to b naught and so on and so forth, local statements, because this approximation does not hold very far away from x naught. That's the trouble. Okay. The proof will tell you that. Okay. Right. So let us continue with the proof of the inverse function theorem. So this proof is highly non-trivial, as you can very well imagine. So let's first prove, for r equals 1, first. What is R again? Let's go back to the statement so that we have not written the statement here, it's written elsewhere. What is the statement again? F is a CR function and the derivative matrix at a point A is invertible, then F is locally invertible and the inverse is also CR. So let's assume F is a C1 function, then we will prove that it's locally invertible and the local inverse is C1. Once we prove it for R equals 1, we can, using mathematical induction on R, prove it for other values of R as well. Okay? So the hardest case is the first non-trivial case, namely R equals 1. Okay. So what does it entail for F to be locally invertible? What do we have to prove really? We need to find a neighborhood V around A so that F from V to F of V is firstly 1 to 1. Secondly, F of V is an open set. Then the inverse does exist and this is an open set. So you can even ask whether the inverse is actually C1 or not. Otherwise, it doesn't even make sense to talk about differentiability if this were not open, right? Then we will prove the strategy of the proof. This is the strategy if you wish. You first prove it as find a V so that it's 1 to 1. Shrink the V if necessary so that this is open. Then prove that this is continuous. That's the next step. Then prove that F inverse is actually differentiable, and using the formula for the derivative, prove F inverse is C. Okay, these are the steps. So let's start with this first. Okay. How do you prove that F is locally 1 to 1? Why would you expect this in the first place, right? Well, the rough idea of the proof, which we will make precise in a moment, is f of x is approximately f of x naught plus the derivative of x times x minus x naught, right? So suppose this is equal to b, then b minus f of x naught is approximately this. And because this is invertible, if there is a solution, there will be only one solution because this is invertible. Okay? So that's the rough idea. So in fact, we will prove something stronger. There exists an alpha positive such that f of x naught minus f of x1 of some for some radius r. So as long as you are sufficiently close to A, not only is f 1 to 1, as long as you restrict your attention to a small ball around A, but also you can say something stronger. Why is this stronger? This implies f is 1 to 1 on this ball. Why? Because if f of x naught equals f of x1, then 0 is larger than alpha times mod of x naught minus x1, which means x naught equals x1, which means f is 1 to 1. We are saying something stronger than that. Okay. Why would the stronger thing help? It could potentially, for example, help if whilst proving that f inverse is continuous, okay, for example. Why would you even expect this sort of a thing to be true? This is not obvious, right? So suppose if f of x is ax, that is for linear functions where a is invertible. Why is it true even in this case? Why is, let's call this star, why is star true even in this case? This is also not obvious, right? I mean, what would star say maybe I'll call this an example. What would star say in this particular case? It would say that norm of ax1 minus x2 is larger than this if A is invertible. Why is this true, right? So this is not immediately obvious, right? So suppose that this is of course f of x1, this is f of x2, right? Okay, so how does one prove such a thing? Well, suppose you say y is ax, then A inverse of y is x, right? So then what does this mean? It would mean that, say, x1 minus x2 times, well, maybe let's call this A inverse of y1 minus y2 equals x1 minus x2, right? So that means norm of A inverse of y1 minus y2, which is less than norm of A inverse norm of y1 minus y2, is norm of x1 minus x2, which means norm of f of x1 minus f of x2, which is what y1 and y2 are, is larger than 1 by norm of A inverse norm of x1 minus x2. So this is your alpha, provided you know that norm of A inverse is finite. Why is the norm of A inverse finite? If A is an invertible matrix, why is the norm of A inverse finite, right? This is not immediately obvious. One way to prove it would be as follows. You have an explicit formula for A inverse. A inverse is the so-called cofactor matrix divided by the determinant of A, or maybe some people call it the adjugate matrix or whatever. Basically, it's a matrix whose entries are polynomials in the entries of A divided by the determinant of A, right? If the determinant of A is not 0, then the norm of this, which is equal to the norm of this, is obviously less than a constant times the norm of this numerator, which is of course bounded above. It is finite, right? It's basically a matrix whose entries are polynomials in the entries of A. So surely its norm is bounded above. The only way things can go wrong is if the determinant would have been 0, which it isn't in our case. So in other words, the bottom line is the norm of A inverse, this norm is finite, and therefore you can say that f of x1 minus f of x2, which is equal to y1 minus y2 in our case, is larger than alpha times norm of x1 minus x2, where alpha is 1 divided by norm of A inverse. So even for a linear function, this statement star is not immediately obvious, right? It required work, the work being precisely to show that the norm of A inverse is finite. This is not a trivial statement. To show that A inverse is some matrix divided by the determinant of A, that's not trivial. That's a non-trivial theorem in linear algebra. Okay. There are other ways of doing this also, but this is one way, for example. Okay. The other ways would probably, for instance, one way to do it would be to get things to the row echelon form and so on and so forth. Anyway, the bottom line is, so we know that star is true for linear functions. Happily enough, for nonlinear functions, this much is almost good enough. Okay, right. So first of all, choose R positive so that on the following ball this equation holds. So f of x1 such that x1 and x1 plus h belongs to this, which lies completely in U. First of all, choose R so small that a small ball around A lies completely within U. Now take 2 points x1 and x1 plus h lying in this ball. This is equal to the derivative of x1 at h plus an error term, right? This is the error term. The point is the error term divided by norm h goes to 0 as h goes to 0 by definition of differentiability, really, okay? Okay. Now the point is, choose R to be so small that dfx is invertible. This matrix dfx is an invertible matrix for all x in this, and this matrix inverse norm is less than C for all x in this spot. Right. So we've originally chosen the ball to be so small that it's contained entirely within U. Now we will shrink the radius of this ball so much that this also holds. So the question is, why is this even possible? What we have assumed in the statement of the theorem is merely that this is invertible. Invertible by hypothesis. By hypothesis. That's all we've assumed. So why would that imply that this is invertible, right, for all x sufficiently close to x1? So first of all, what does invertibility of a matrix mean? A matrix is invertible if and only if the determinant is not 0. But the determinant of a matrix is a continuous function in the entries of the matrix. It's a polynomial, no less. So in other words, this function is continuous too. Why is it continuous? Because it's a composition of two continuous functions. We've already assumed that the derivative matrix is a continuous matrix valued function of x. That's the assumption of being C1, by the way. And the determinant is a continuous function of matrices. The composition of these two is a continuous function. And therefore, if the determinant of df at x1 is non-zero, it continues to be non-zero as long as x is close enough to, close in, so this is not invertible. What we mean is dfa is invertible by hypothesis. I'm sorry, this is not yet true. Okay, let me erase this. All right. So dfa is invertible by hypothesis. So the determinant of df at the point A is non-zero. By continuity, this determinant continues to be non-zero on a small ball around A. Therefore, df is invertible in a small ball around A. Why is this true? Note that, again, the map from x to this inverse is also continuous. Why is it continuous? Because we have an explicit formula for the inverse of a matrix. It's equal to, as I just wrote here, a matrix whose entries are a polynomial in the entries of A divided by the determinant of A. This is Cramer's formula, or Cramer's rule, if you will. Okay. Obviously, entries of polynomial functions of A are continuous. The 1 by determinant is a continuous function as long as the determinant is non-zero. So this is a continuous function, and a continuous function on a compact set is bounded. So if necessary, shrink your R enough so that, let's say, a ball, so that the closed ball are, so you can shrink your R to be so small that in fact the derivative is not just invertible on the open ball, it's actually invertible on the closed ball, and closed bounded subsets are compact, and therefore this is bounded above. Okay. Okay. So in other words, as long as you're within this ball, this is invertible and the derivative of this inverse is bounded above. Okay. Right. This is only to say that f of x is very close to being a linear function. That's all I'm trying to say in simple terms. Okay. Right. So in other words, so once again, let me write this down. So if you multiply by the inverse of this matrix, by the way, I didn't put vector symbols. If you wish, if that makes your intuition sharper, you can do it, but I'm not doing this. Okay, it's understood. Times delta. Yeah? All right. Which means that norm of x1 plus h times c is larger than this. Why? Because the norm of this is equal to the norm of this, and this is less than or equal to this. Why? Because we've already stated this. We've chosen R to be so small that this happened. So in other words, times, then what can we say? This is larger than norm h minus norm of this. Right? So this is norm h by c, 1 minus this much. Right. Now what can we say? Notice that what property does this error term satisfy? The error term divided by norm h goes to 0 as h goes to 0. Right? So, as a consequence, what we can say is norm of df x1 inverse times delta divided by norm h is less than c. Okay? This is less than half if h is sufficiently small. Right? Because delta divided by norm h goes to 0 as h goes 0. In other words, by shrinking R further if necessary on BA of R, which is contained in U, what we have is that norm of f of x1 plus h minus f of x1 is larger than this. Right? Where alpha is 1 divided by 2c. Okay? Because this is less than half, so 1 minus this is larger than half. Right? So that proves that f is not only locally 1 to 1, but also this rather strong statement holds. Okay? Right. So at least we have shown that f is locally 1 to 1. Okay? By linear approximation, showing it first for linear things, and there we use the explicit formula for the inverse of a matrix, namely Cramer's rule, right? Which is a non-trivial matter, of course. And after that, one just has to keep track of things carefully, right? The next time, so we'll of course, we'll stop right now, but the next time we will continue, and we will show that, in fact, so far what have we shown? We have shown that f is locally 1 to 1, right? The next step of the strategy would be to show that there is a neighborhood around f of a for which f is onto that neighborhood. Okay? That is the most delicate part of the proof, right? So we'll do that the next time. Okay. So thank you for joining.